Galaxies are crashing into each other in the depths of space. This is not a story of destruction, but the hidden creative force that built our universe. By the end of this, you will understand why these cosmic collisions are essential to everything we see in the night sky. We will uncover how dark matter orchestrates these events and what happens when supermassive black holes decide to merge. What does it mean for our own galaxy to be on a collision course with its neighbor? The scale of the cosmos defies human intuition. The emptiness between galaxies is so profound that a direct crash seems almost impossible. Yet these titanic meetings happen all the time. The secret lies in the universe's hidden architecture, a structure known as the cosmic web. Picture an unimaginably vast spider's web stretching across the entire observable universe. The shimmering strands of this web are not made of silk, but of dark matter, an invisible substance that exerts a powerful gravitational pull. Galaxies are not scattered randomly. They are strung along these dark filaments like glittering jewels on a necklace. Where these strands intersect, they form immense clusters, gravitational metropolises where hundreds or even thousands of galaxies are gathered. Inside one of these clusters, galaxies are not truly isolated. They are all orbiting a common center of gravity, a dense core dominated by the combined pull of dark matter and the largest galaxies. Think of it as a cosmic dance floor, but one where the dancers are moving in slow motion over billions of years. Their gravitational tugs are constant, a relentless force that subtly alters their paths. Over cosmic time, these gentle nudges can draw two galaxies closer and closer, setting them on a collision course that unfolds over eons. The apparently empty space is not a void. It is a dynamic arena where gravity is always at work, continuously negotiating the fate of every star system within it. This grand design makes galactic collisions not a freak accident, but an inevitable part of the life cycle of the universe. This silent music of gravity is a force of incredible patience. While we experience it as the pull that keeps our feet on the ground, its true power is revealed across the unimaginable voids between galaxies. It operates on a timescale that dwarfs human history, a slow, relentless tug that never ceases. Sir Isaac Newton first gave us the mathematics to describe this pull, showing how every object in the universe attracts every other object. But it was Albert Einstein who revealed the stunning mechanism behind it. He proposed that gravity is not a mysterious force reaching across space, but rather a curvature in the very fabric of the universe. Imagine placing a heavy bowling ball in the center of a stretched rubber sheet. The ball creates a deep well. Now roll a marble near the edge of that well. The marble will not travel in a straight line. It will curve inward, spiraling towards the bowling ball. This is a simple analogy for Einstein's theory of general relativity. Massive objects like stars and galaxies warp the space-time around them. Other objects moving through this warped space simply follow the curves, the paths of least resistance. A galaxy does not actively pull another galaxy toward it. Instead, it creates a gravitational depression in the cosmos, and its neighbors fall into that depression over billions of years. This is the invisible choreography that orchestrates the entire cosmic dance. Without this persistent, shaping force, the glittering jewels of the cosmic web would never find each other. They would drift forever in the dark, silent and alone. But gravity ensures the dance continues, setting the stage for the spectacular collisions that reshape the universe. And when these titans finally meet, the encounter is far more graceful and strange than a simple crash. This cosmic glue is a substance we cannot see, touch, or directly measure, yet it dictates the motion of galaxies. Dark matter is the universe's greatest phantom, a ghost that makes its presence known only through its immense gravitational pull. It makes up the overwhelming majority of matter in the cosmos, about 85% of it. Think of a galaxy not as a simple disk of stars, but as a tiny, glittering city at the heart of an invisible, sprawling metropolis. This metropolis is the dark matter halo, a vast, spherical cloud that envelops the entire visible galaxy. Its gravitational reach extends far beyond the last visible star, creating a deep and wide well in the fabric of spacetime. When two galaxies drift near one another in the cosmic web, it is these enormous dark matter halos that make first contact. Their invisible tendrils of gravity intertwine, pulling and tugging long before the stars themselves ever get close. This is why the dance begins in the dark. The luminous stars and glowing gas we see in telescopes are merely passengers caught in a gravitational tug of war orchestrated by these unseen giants. Without the immense additional gravity provided by dark matter, the visible mass of a galaxy would be far too weak to reliably pull other galaxies into a merger across such vast distances. The dark matter halo acts as a cosmic anchor, dramatically increasing the gravitational reach of a galaxy and ensuring that a close pass often becomes an inescapable embrace. So when we witness two galaxies colliding, we are only seeing the final, luminous act of a drama that began billions of years earlier in the realm of the invisible. These galactic orbits are the second great engine of cosmic collision. Every galaxy within a vast cluster is in motion, tracing a slow, majestic path around the cluster's gravitational heart. But these paths are not the neat, circular orbits of planets around a star. They are far more chaotic, stretched into long, looping ellipses that send galaxies diving inward and soaring outward over billions of years. Add to this the constant, subtle gravitational tugs from every other galaxy in the neighborhood, and you have a recipe for orbital instability. A galaxy's path is continuously perturbed, its trajectory slowly changing in a cosmic dance of push and pull. Given enough time, and the universe offers near limitless amounts of it, these perturbed orbits will inevitably bring galaxies into close proximity. It is a matter of statistical certainty. With so many galaxies moving in a confined space over such immense timescales, close encounters and direct mergers become not just possible but unavoidable. Picture a game of billiards played on a table the size of the observable universe, where the balls are entire galaxies. The cue stick is gravity itself, and every shot takes a billion years to complete. The paths these galactic balls trace, their wild elliptical journeys, are the first slow-motion steps toward a transformative meeting that will reshape them forever. So how do we witness a dance that takes longer than the existence of life on our planet? Astronomers become cosmic detectives, piecing together the story from a single, frozen moment in time. We cannot watch a galaxy collision in real time, as these events unfold over hundreds of millions of years. Instead, we rely on the subtle clues they leave behind. The most fundamental clue comes from the light of the galaxies themselves. By analyzing this light with immense precision, scientists can detect a subtle stretching or squeezing of its waves, known as redshift and blueshift. If a galaxy is moving away from us, its light waves are stretched, making them appear redder. If it is moving toward us, the waves are compressed, shifting toward the blue end of the spectrum. This is the cosmic version of hearing the pitch of a siren change as an ambulance races past you. By meticulously mapping these shifts across the sky, astronomers can reconstruct the velocities and trajectories of entire galaxies, revealing which ones are on a fateful approach. But knowing their paths is only part of the puzzle. To understand what happens next, we turn to the power of prediction. Supercomputers run incredible simulations, digital universes governed by the unbreakable laws of physics. They input the known masses, speeds, and positions of two approaching galaxies, and then let gravity do its work. The simulation fast-forwards through millions of years of cosmic evolution in a matter of days, showing us the most probable outcome of the collision. These digital prophecies have accurately reproduced the strange and beautiful shapes we later observe with our telescopes. And what do those observations reveal? Different types of light tell different parts of the story. Optical telescopes show the distorted shapes and the brilliant, tangled star trails. Radio telescopes peer through cosmic dust to see vast reservoirs of gas being compressed and agitated. X-ray telescopes reveal the superheated materials swirling around the awakening supermassive black holes at the galaxy's hearts. Each wavelength is like a different voice telling its part of the same epic tale. From this symphony of data, we can decipher the invisible forces at work, a stunning achievement that allows us to see the future written in the sky. The first brush of these cosmic titans is a spectacle of slow-motion grace. As two galaxies drift into each other's gravitational influence, their initial encounter is not a violent crash, but a profound and elegant distortion. Their immense gravity begins to sculpt the space between them, creating a bridge of invisible force. The outermost stars and nebulae, those farthest from the gravitational anchor of their galactic cores, are the first to respond. They feel the rival pull and they begin to drift slowly at first, then with increasing purpose away from their home. This is the birth of the tidal tails, immense rivers of stars and glowing gas that stream out from the galaxies, forming sweeping, luminous arcs that can stretch for hundreds of thousands of light years. These are not trails of destruction, but beautiful signatures of the immense, unseen forces now at play. The galaxies themselves begin a gravitational dance, often swinging past each other in a wide, looping orbit. They exchange energy and momentum in this cosmic slingshot, a maneuver that can alter their trajectories forever. It is a delicate and prolonged courtship, a first touch that sets the rhythm for all the dramatic steps to come. These beautiful tidal tales are just the beginning of a deeper structural upheaval. As the gravitational dance continues, the very identity of a galaxy is rewritten. The elegant spiral arms, those grand designs that define so many galaxies, begin to unravel. For billions of years, these arms were stable structures, held together by a delicate balance between the inward pull of gravity and the outward force of orbital motion. But the intruding galaxy's gravity acts like a giant, invisible hand, reaching in and stirring the entire system. This external pull creates immense tidal forces, stretching and shearing the galactic disk. The orderly rotation of billions of stars is thrown into chaos. Their neat, circular orbits are perturbed into wild, overlapping ellipses, creating a gravitational traffic jam of cosmic proportions. The once flat disk becomes warped, bending and twisting like a piece of cosmic parchment caught in a storm. In some collisions, the central bulge of a galaxy can be yanked into a ring, a perfect circle of frantic star formation. In others, the entire structure is pulled into a lopsided, irregular mess, a formless cloud of stars that bears no resemblance to its original self. This morphological transformation is a battle of titanic forces. The galaxy's own gravity struggles to hold its shape, but the overwhelming tidal forces from the collision are simply too powerful. The familiar becomes alien in a relatively short cosmic moment. Yet within this apparent destruction lies a profound creativity. The galaxy is not being erased, it is being remixed, its stars and gas rearranged into entirely new and unique architectural forms. These temporary, chaotic shapes are the blueprints for the future, a necessary phase of turmoil before a new, stable galaxy can emerge from the cosmic wreckage. This cosmic remodeling is governed by an unbreakable rule of physics, the conservation of angular momentum. In simple terms, angular momentum is the spin of an object, a measure of its rotational motion. A figure skater pulling her arms in to spin faster is a perfect example. She is conserving her angular momentum. When two galaxies collide, they bring their own immense spins into the mix, and the total amount of this spin must be preserved. It cannot be created or destroyed, only transferred and redistributed. This law dictates the final form of the merged galaxy. If the two original galaxies were spinning in the same direction, their combined angular momentum can create a new, rapidly rotating core, a dense stellar hub spinning at incredible speeds. But if their spins were opposed or wildly different, the conservation law demands a different outcome. The conflicting rotational energies cannot simply cancel out. Instead, the excess momentum is often flung outward, catapulting stars and gas into vast, looping orbits that create the spectacular shells and halos we observe around many elliptical galaxies. This is not chaos, but a complex and precise negotiation. The merger is a gravitational ballet where every star, every cloud of gas, is part of a grand calculation to balance the books on rotational energy. The final architecture of the new galaxy, whether it becomes a fast-spinning ellipsoid or a more disordered swarm, is the direct result of this cosmic accounting. It is the universe finding the most stable configuration, the perfect shape to hold all that inherited motion. The most brilliant consequence of this cosmic chaos is a sudden, spectacular firestorm of creation. As the galaxies intertwine, their colossal clouds of interstellar gas and dust do not simply drift past one another. They slam together. Imagine two immense, cosmic weather fronts colliding, their swirling masses of hydrogen and helium compressed by immense tidal forces and powerful shock waves rippling through the galactic structure. This compression is the ultimate cosmic trigger. These giant molecular clouds, once stable and diffuse, are suddenly squeezed beyond their ability to resist their own gravity. They begin to fragment and collapse, each collapsing, not igniting into a blazing new star. This is the genesis of a starburst, a ferocious wave of star birth that can transform the entire character of a galaxy. In a relatively short cosmic timespan, perhaps just a few tens of millions of years, millions upon millions of new stars flare into existence. The galaxy becomes a celestial fireworks display, with entire clusters of massive, blue-white stars igniting in a synchronized burst of light. These starburst regions shine with such ferocious intensity that they can outshine all the billions of older stars in the galaxy combined. We see this breathtaking process unfolding in systems like the famous Antennae Galaxies. In telescopic images, they are not just two distorted shapes, they are studded with brilliant pinkish knots. Each of those knots is a vast stellar nursery, a region where thousands of new stars are being born simultaneously, their intense ultraviolet radiation causing the surrounding gas to glow like a cosmic neon sign. This prolific phase is both magnificent and temporary. The very fuel for this fire is rapidly consumed. The largest of these new stars are profligate giants, burning through their nuclear fuel in only a few million years before exploding as supernova. These violent deaths then seed the surrounding space with heavy elements and trigger yet more waves of star formation in a cascading cycle of creation and destruction. A galactic collision, for all its destructive appearance, becomes the universe's most powerful engine for forging new solar systems and enriching the cosmos with the very elements that make planets and life possible. It is the ultimate act of cosmic alchemy, turning the chaos of a gravitational wreck into a brilliant, if fleeting, beacon of light. But this stellar fireworks display is only one act in the grand play. At the very heart of this cosmic merger, something far darker is stirring. Nestled in the core of nearly every large galaxy is a supermassive black hole, an entity of such immense gravity that not even light can escape its grasp. When two galaxies collide, their central black holes are pulled into the newly forming gravitational center. At first, they may simply orbit one another, a binary pair of invisible titans circling in the darkness. This is a dance of ultimate extremes where each partner is a gravitational singularity millions of times heavier than our Sun, but their waltz is not eternal. As they plow through the dense fog of stars and gas now concentrated in the galactic core, they experience a kind of friction, a dynamical drag that slowly saps their orbital energy. This loss of energy forces them to spiral ever closer, tightening their orbit over millions of years. This slow, inward spiral is a prelude to one of the most violent events in the universe, a collision between the two most destructive objects nature can create. When they finally merge, they do not crash in a conventional sense. Instead, they ripple the very fabric of reality. Their cataclysmic union sends powerful gravitational waves racing out across the cosmos, distortions in spacetime itself, just as Albert Einstein predicted. But before that final, silent crash, these black holes can unleash a different kind of fury. As they draw near, the chaotic environment feeds them. Vast amounts of gas, compressed and heated to millions of degrees by the galactic collision, swirl into accretion disks around one or both black holes. This infalling material does not cross the event horizon quietly. It is superheated to incredible temperatures, glowing with intense radiation across the entire electromagnetic spectrum. In this state, the black hole system becomes an active galactic nucleus, a cosmic beacon that can outshine every star in its galaxy combined. Some of these active nuclei erupt, shooting out colossal jets of energy and particles at nearly the speed of light, carving through intergalactic space for thousands of light years. This violent output can heat and blow away the surrounding gas, effectively shutting down the very starburst that gave it birth. The dance of the galaxies is therefore mirrored by a dance of their darkest inhabitants, a gravitational tango that can either fuel a galaxy's rebirth or starve it of its future. The fate of the entire merged galaxy is, in many ways, decided by the final, silent merger of these two invisible hearts. This gradual loss of energy is the universe's way of ensuring a permanent union. While the initial encounter is a graceful swing, the galaxies do not simply fly past each other into the void. An unseen force, a cosmic friction, begins to slow their grand orbital dance. This is not friction in the everyday sense of two surfaces rubbing together, for the emptiness of space offers no such resistance. Instead, it is a gravitational phenomenon known as dynamic friction. As the two galaxies interpenetrate, their countless stars and vast dark matter halos pass through one another. Each star, though distant from its neighbors, exerts a tiny gravitational pull on the stars of the other galaxy. Think of it as a cosmic crowd moving through another cosmic crowd. Every individual exerts a slight pull on those passing by, and the combined effect of trillions upon trillions of these minuscule tugs creates a net drag force. This gravitational drag acts as a brake, steadily siphoning orbital energy from the system. The galaxies lose momentum, their wide, looping orbits beginning to decay. They spiral closer and closer, their fate now sealed by this relentless, invisible grip. It is similar to a spacecraft dipping into the upper atmosphere. The sparse molecules of air are not a solid wall, but their cumulative impact is enough to create friction, slowing the craft and causing its orbit to decay until it is committed to a final descent. In the galactic context, this dynamic friction ensures that a close pass becomes an inescapable embrace. The dance partners, having felt each other's pull, are now destined to become one, their separate identities dissolving into a new, larger system that will bear the marks of their magnificent collision for billions of years to come. From the wreckage of these galactic collisions, entirely new worlds are born. As immense tidal tails stream out into intergalactic space, they are not just simple trails of debris. Within these rivers of stars and gas, something remarkable can happen. Dense pockets of material begin to coalesce, their own self-gravity pulling them together into tight, glowing knots. These are not just star clusters, they are tidal dwarf galaxies, entirely new and independent islands of stars forged in the chaos of the merger. Imagine a massive construction site where the demolition of two old skyscrapers sends rubble flying, and from that flying debris, several small, fully formed houses spontaneously assemble themselves in midair. That is the essence of a tidal dwarf galaxy. They are cosmic phoenixes rising from the expelled material of their parents, but these newborns hold a profound secret that sets them apart. They are made almost entirely from the visible, ordinary matter we can see, stars and gas. Their parent galaxies, however, are anchored by immense halos of dark matter, the invisible gravitational glue that holds them together. During the violent collision, that dark matter behaves differently. It is more diffuse and less affected by the tidal forces, so it largely stays with the central, merging cores. The visible gas and stars, however, are easily stripped away, and it is from this purer, dark matter-free debris that the tidal dwarfs form. This makes them unique natural laboratories. Studying them helps astronomers understand the properties of ordinary matter in isolation, without the overwhelming gravitational influence of dark matter to complicate the picture. Their very existence adds a stunning layer of irony to the cosmic dance. The same event that tears apart the grand architecture of two massive galaxies can, in the same breath, sow the seeds for new, smaller ones. These tiny celestial offspring then drift away, each one a permanent testament to the creative power of a collision, a living memory of the day two giants became one. Yet for all the violence of this stellar rearrangement, the true metamorphosis happens in the cold, dark clouds between the stars. The vast emptiness within a galaxy is not truly empty. It is filled with an incredibly diffuse sea of gas, mostly hydrogen. While the stars themselves are so far apart they almost never physically strike one another, these immense gas clouds have no such luxury. They are colossal, spanning light years, and when two galaxies intertwine, these gaseous frontiers are the first to make contact. The resulting collision is not a silent merging, but a cosmic cataclysm. These giant clouds slam into each other at speeds of hundreds of kilometers per second. The impact generates powerful shock waves, immense walls of compressed energy that rip through the interstellar medium. Think of two weather systems on a planetary scale colliding to create a hurricane of unbelievable ferocity, but here the storm is made of pure hydrogen and helium. These shock waves force the gas into a frenzied dance, squeezing it from all sides, ramming its atoms together with unimaginable force. This violent compression is the universal trigger. It pushes the gas past a critical threshold, a density where its own self-gravity can no longer be resisted. The clouds begin to collapse, fragmenting into thousands of dense, glowing knots. Each knot is a stellar womb, a protostar igniting under the pressure of its own birth. This is the engine behind the spectacular starbursts we witness, the reason a merging galaxy can suddenly blaze with the light of millions of newborn suns. Without this rich, gaseous fuel, a galactic collision would be a far darker, quieter event. We would see the graceful tidal tails and the distorted shapes, but we would miss the brilliant, pinkish glow of stellar nurseries and the fierce blue light of young star clusters. The gas is the essential ingredient, the raw material that turns a gravitational drama into a brilliant firestorm of creation, forging the very building blocks for new worlds and perhaps new possibilities for life itself. This final transformation is the most profound outcome of the cosmic dance. The elegant, spinning spiral galaxy, with its graceful arms and busy star-forming regions, is fundamentally remade. Its identity is erased, replaced by the serene, featureless form of an elliptical galaxy. This metamorphosis is not a random outcome. It is the direct and inevitable result of the violent gravitational forces unleashed during a major merger. A spiral galaxy is a delicate equilibrium, a rotating disk where stars follow orderly, circular paths. This organized motion is the galaxy's defining characteristic. But when another massive galaxy smashes through this delicate structure, that order is shattered. The intruder's gravity introduces chaos, violently stirring the stellar population. The stars are flung onto new, random, and overlapping orbits, like a swarm of bees replacing a well-rehearsed ballet. The galaxy's rotation is effectively cancelled out, its spin energy transformed into the random, jostling motions of its constituent stars. The result is no longer a flat disk, but a rounder, puffier, three-dimensional swarm. This new structure is held together not by rotation, but by the collective pressure of all those stars moving in every direction, a state astronomers call pressure-supported. The galaxy has been fundamentally rebooted, but the transformation does not stop with the stars. The spiral galaxy's rich reservoirs of gas, the raw material for new stars, are either rapidly consumed in the brilliant but brief starburst or violently expelled. Supernova explosions and fierce radiation from the newly active black holes blow the remaining gas clear out of the galaxy, starving it for fuel. Without this cool gas, the new elliptical galaxy cannot form new stars in any significant number. It becomes a quiet, aging stellar retirement community, filled with older, redder stars, its days of vibrant creation long behind it. This is the ultimate evidence for a powerful idea known as hierarchical formation, the concept that the largest structures in the universe, like giant elliptical galaxies, were built from the mergers of smaller ones. The dance does not just rearrange the dancers, it forges them into an entirely new being, a cosmic phoenix rising from the collision in a form that will last for billions of years. This cosmic dance is not just a spectacle for distant galaxies, it is the written destiny of our own Milky Way. For decades, we looked upon the Andromeda galaxy as a serene, spiraling neighbor, but precise measurements have revealed a startling truth. We are on a direct collision course. The Hubble Space Telescope has tracked the motion of Andromeda with immense precision, confirming that in about 4.5 billion years, our two great spiral galaxies will begin their first close pass. This is not a possibility, it is a forecast written in the motions of the stars themselves. The Sun and its planets will be along for the ride, likely flung into a new, wider orbit within the merged galaxy. Yet, against this backdrop of galactic upheaval, our solar system will probably remain intact, a tiny life wrapped in a sea of stellar chaos. The sheer emptiness of space means our Sun and its neighboring stars are unlikely to crash into one another. The real drama will unfold in the skies above any future world. As the galaxies draw nearer, Andromeda would grow from a faint smudge into a brilliant, sprawling tapestry of light, eventually filling the entire night sky. The familiar band of the Milky Way would be joined and then twisted by the approaching giant, a celestial ballet of unimaginable scale playing out overhead for billions of years. The merger will ignite a firestorm of star birth, a final, glorious starburst as the galaxy's gas clouds collide and collapse. This brilliant but fleeting era of creation will eventually consume the remaining star-forming fuel. The two elegant spirals, their structures shattered by the gravitational turmoil, will settle into a single, vast entity, a giant elliptical galaxy often nicknamed Milky. Our home galaxy, as we know it, will be gone, transformed into something entirely new and serene. This future event transforms abstract cosmic theory into a deeply personal story. It shows us that the great collisions that build the universe are not just something that happens to others, but are an intimate part of our own galactic heritage, a slow-motion future already in motion. These digital prophecies are born from some of the most powerful computers on Earth. To witness a galactic merger from start to finish, astrophysicists construct entire universes inside their machines. They begin by defining two galaxies, not as continuous disks of light, but as vast collections of digital points, often millions or even billions of them. Each of these points is a simulated particle, a stand-in for a swarm of stars, a clump of dark matter, or a cloud of interstellar gas. This is the essence of an n-body simulation, a colossal computational problem where every single particle gravitationally influences every other particle. The computer's task is to calculate this unimaginable web of attractions, trillions upon trillions of individual forces, and then nudge every particle forward in time by a tiny fraction of a second. It then recalculates everything and takes another step, repeating this process over and over until billions of years of cosmic evolution have unfolded on the screen. The physics governing this digital cosmos is uncompromising. The immutable law of gravity dictates every tug and pull. For the gas particles, the simulation adds the complex rules of hydrodynamics, modeling how these cosmic clouds compress, shock, and swirl as they collide. Watching one of these simulations play out is like watching a slow-motion film of a dance we could otherwise only see a single frame of. The initial spiral galaxies swing past each other, their disks warp, and majestic tidal tails erupt outwards, all driven by the relentless calculation of physical laws. The true power of this method lies in comparison. Scientists can run a simulation with a specific set of starting conditions, then compare the final, merged galaxy it produces to a real one observed by the Hubble Space Telescope. If the shapes match, if the stellar streams align, it confirms that our understanding of the underlying physics is correct. If they do not match, it sends the scientists back to their digital drawing board, forcing them to refine their models, perhaps by adjusting the role of dark matter or the feedback from exploding stars. These virtual laboratories are our only window into the complete story of a galactic merger, allowing us to rewind and fast-forward through cosmic time to decode the beautiful violence that builds the universe. This brilliant firestorm of creation holds within it the seeds of its own end. The universe has built in a powerful self-regulating mechanism, a cosmic feedback loop that prevents galaxies from burning too brightly for too long. When a collision triggers a ferocious starburst, it does more than just light up the cosmos. Those millions of new, massive stars are incredibly violent and short-lived. They flood their surroundings with intense ultraviolet radiation and generate powerful stellar winds, streams of charged particles that rush outward like a constant hurricane. This relentless output acts like a giant cosmic hairdryer, blasting the surrounding clouds of gas. The gas does not gently cool and form more stars. It is heated to such high temperatures that it cannot easily collapse anymore. It is effectively sterilized, rendered infertile for future star formation, but the feedback does not stop there. At the very heart of the merger, the supermassive black holes, now feeding on the infalling gas, add their own overwhelming voice to the chorus. As an active galactic nucleus, they can erupt, shooting out jets of energy and radiation that carve through the galaxy. These jets inject so much turbulence and heat into the remaining gas reservoirs that they can blow it all clear out of the galaxy entirely. This is the ultimate act of self-regulation. The very processes that a galactic collision ignites, the starbursts and the black hole activity, eventually work to shut themselves down. They quench the fire by removing the fuel. This feedback ensures the cosmic dance has a rhythm, a natural cycle of boom and quiet. Without it, a merging galaxy would rapidly and inefficiently turn all of its cosmic gas into a single, brief generation of stars, leaving nothing for the future. Instead, feedback spreads out the process, governing the final mass and size of the newly formed elliptical galaxy. It is a balancing act of breathtaking scale, where creation and destruction are two sides of the same coin, ensuring that the universe avoids total chaos and finds a stable, enduring form. A living textbook of a galactic collision unfolds just 45 million light-years away. The Antennae Galaxies are our front row seat to the cosmic dance, a pair of spirals caught in a magnificent, destructive embrace. Their name comes from the two long, sweeping arcs of stars that stream into the darkness, resembling the delicate antennae of some colossal insect. These are the iconic tidal tails, formed when the galaxies first swung past each other hundreds of millions of years ago, their outer stars ripped away by gravitational forces and flung into intergalactic space. That initial encounter was merely the first step, and now the main act is underway. The two galactic cores are drawing closer, their shapes already twisted and distorted beyond recognition. What was once a pair of elegant spirals is now a tangled, glowing knot of stellar chaos. Within this knot, the Hubble Space Telescope has revealed a breathtaking sight, over 1,000 brilliant clusters of newborn stars shining like diamonds scattered on black velvet. Each cluster contains millions of young, hot stars, all born from the violent compression of colliding gas clouds. The entire system is ablaze with the pinkish glow of hydrogen, a telltale sign of rampant star formation, while supernova explosions dot the scene, clearing away the cosmic dust and seeding space with heavy elements. The Antennae Galaxies are not a static picture. They are a dynamic snapshot of a universe in flux. By studying this nearby laboratory, astronomers can watch the processes we have theorized about unfold in real time, from the triggering of starbursts to the complex dynamics of gas and dust. This is where abstract simulation meets observable reality, confirming that the beautiful violence we model in computers is indeed the creative force that forges new galaxies across the cosmos. These vast stellar halos are the ghostly footprints of ancient collisions. When galaxies merge, the conservation of angular momentum flings countless stars not into the tidy central disk, but out into the deep, dark frontier. They are catapulted into immensely wide, looping orbits, creating a gigantic, spherical cloud that can extend hundreds of thousands of light-years from the galactic center. This halo is incredibly faint, its stars so sparsely scattered that it appears almost transparent against the blackness of space. Yet within this faint glow lies a cosmic archive, a fossil record written in starlight. The chemical composition and orbital paths of these exiled stars tell a clear story. They are often older and made of different elemental mixtures than the stars in the galaxy's main disk, revealing that they originated in other, smaller galaxies that were torn apart and absorbed. Our own Milky Way possesses such a halo, and by studying its stars, astronomers have identified distinct streams and clusters that are the shredded remains of dwarf galaxies consumed over billions of years. This is the ultimate evidence for hierarchical growth, the slow, relentless process where a large galaxy like ours is built by devouring its smaller neighbors. Each merger, no matter how small, contributes stars to this growing halo, layer upon layer. The beautiful spiral we see on a clear night is merely the bright, ordered core of a far grander and more chaotic structure, a structure built from the echoes of countless cosmic dances. These halos are not just debris, they are the enduring memory of a galaxy's violent and creative past, a permanent signature of the collisions that shaped it. But what does this cosmic remodeling mean for the small, quiet neighborhoods around individual stars? The fate of planetary systems like our own solar system is not one of fiery annihilation, but of profound and lasting change. When galaxies intermingle, the sheer emptiness of space is your greatest protector. The average distance between stars is so immense that the chance of two suns physically colliding is almost zero. Your star is far more likely to sail through the galactic merger unscathed. The real danger and the real transformation comes from an invisible source. The chaotic gravitational forces that warp the entire galaxy do not spare its individual inhabitants. As stars are thrown onto new, random orbits, their planets are taken along for the ride. This gravitational turbulence can be so violent that some stars receive a powerful slingshot effect, a kick so strong it can eject them, and their entire entourage of planets completely out of the galaxy. These stars become cosmic castaways, doomed to drift forever in the cold, dark emptiness between galaxies, their planets orbiting a sun that will never again be part of a stellar community. For other solar systems, the journey is less extreme but no less transformative. A star might be nudged into a new, wider orbit within the merged galaxy, perhaps sent from the bustling inner disk to the sparse outer halo. From a planet's perspective, the familiar night sky would slowly unravel. The constellations we know, patterns dependent on our specific location in the Milky Way, would be stretched and pulled apart over millions of years. The brilliant band of our galaxy would distort, replaced by a new, chaotic tapestry of light as the merging galaxy looms ever larger. And while the planets would likely hold their tight orbits around their sun, their long-term stability is not guaranteed. A close gravitational encounter with another star, now more probable in the dense core of a newly forming elliptical galaxy, could theoretically perturb the outer planets, sending them spiraling away or into new, unstable paths. The cosmic dance, for all its grand scale, reaches down to touch every single world, reshaping their celestial environment and rewriting their sky forever. These chaotic mergers are the universe's primary engine for growth and change. In the deep past, our cosmos was a very different place, filled with a countless swarm of small, primordial galaxies. They were the building blocks of everything we see today. Collisions were the routine method of construction, a relentless process of accumulation that astrophysicists call hierarchical assembly. Picture a vast cosmic construction site where small galactic bricks constantly slammed together, fusing into larger and larger structures over billions of years. Our own Milky Way is a product of this ancient history, its current grandeur the result of digesting dozens of smaller galaxies. Without this foundational process, the universe would be a far quieter and simpler place, a scattered sea of undeveloped dwarfs with no grand spirals or immense ellipticals to adorn the darkness. But the influence of these collisions extends far beyond the galaxies themselves. Each violent merger acts as a powerful recycling plant for cosmic material. The ferocious starbursts they trigger create millions of massive stars that live fast and die young, exploding as supernova. These stellar explosions forge heavy elements like carbon, oxygen, and iron, and then blast them out into the void. This enriched material doesn't just stay within its home galaxy. It is ejected by galactic winds and shockwaves, polluting the vast tracts of space between galaxies. This intergalactic medium, once a pristine soup of hydrogen and helium, becomes seeded with the very elements necessary for rocky planets and, ultimately, life. The collisions also dictate the growth of the universe's most mysterious objects. Supermassive black holes at the centers of merging galaxies are fed by the incoming torrents of gas, growing in mass and power with each cosmic union. This intimate link between galaxy mergers and black hole activity suggests a co-evolution, a shared destiny written in the fire of collision. The grand cosmic structures we observe, from the majestic shapes of individual galaxies to the immense clusters they call home, are all monuments to this relentless creative force. The dance of destruction is, in truth, the dance of creation itself. This final, silent crash between two supermassive black holes does not produce a flash of light or a burst of radiation we can see. Instead, it unleashes a vibration, a deep, resonant hum that shakes the very foundations of the cosmos. These are gravitational waves, ripples in the fabric of spacetime itself, first predicted by Albert Einstein over a century ago. When two black holes spiral into each other, their immense masses whip the surrounding spacetime like a spoon stirring a vast cosmic honey. The resulting waves propagate outward at the speed of light, stretching and compressing everything in their path, a distortion so minuscule it requires the most sensitive instruments in history to detect. For stellar mass black holes, we have already captured these signals with ground-based observatories like LIGO and Virgo. But the waves from supermassive black holes, born from the hearts of colliding galaxies, are a different beast entirely. They are not high-pitched chirps, but low-frequency rumbles with wavelengths so long they can span entire solar systems. These waves oscillate over periods of years, even decades, making them impossible to detect from the surface of our planet, which is itself too seismically noisy. To listen for this deep cosmic music, we must go to space. The Future Laser Interferometer Space Antenna, or LISA, is a mission designed for this very purpose. It will consist of 3 spacecraft flying in a perfect triangular formation millions of kilometers apart, connected by laser beams. As a gravitational wave passes through, it will ever so slightly alter the distance between these spacecraft, a change smaller than the width of an atom. By monitoring these infinitesimal shifts, LISA will effectively tune its ears to the lowest registers of the universe's symphony. What would we hear? The final moments of a black hole merger would produce a rising tone, a chirp that grows in both frequency and amplitude as the black holes complete their last frantic orbits before merging into one. This signal would be a direct soundtrack to the climax of a galactic collision, a pure, unadulterated recording of gravity at its most extreme. It would tell us the masses of the black holes, their spins, and even the distance to the event, offering a new sense to explore the cosmos. The dance of the galaxies, for all its visual splendor, has always been a silent movie. With the coming ability to detect these waves, we will finally hear its music. This brilliant firestorm of creation often plays out behind a thick, cosmic curtain. The same dense clouds of gas and dust that collapse to form new stars can also act as a brilliant smokescreen, shrouding the most dramatic events of a galactic merger from our view. In the chaotic core of a colliding galaxy, vast quantities of cosmic soot are stirred up, creating an impenetrable fog that blocks visible light. The very stellar nurseries and feeding black holes we most want to see become hidden, their intense optical light absorbed and re-radiated as invisible heat. To lift this veil, astronomers must change their perspective, turning to eyes that see in the dark. Infrared telescopes are the key. Just as night vision goggles allow you to see heat signatures in total darkness, these instruments detect the longer wavelengths of infrared light, which are far less affected by dust. The dust itself glows warmly in these wavelengths, revealing the hidden structures in stunning detail. This is where the James Webb Space Telescope has become a revolutionary tool. Its powerful infrared vision can peer directly into the heart of a galactic collision, seeing through the dust to reveal the brilliant clusters of newborn stars and the swirling gas around supermassive black holes that were completely invisible to previous telescopes like Hubble. Radio telescopes provide another crucial viewpoint, their long waves passing effortlessly through the obscuring clouds to map the distribution of cold hydrogen gas, the raw fuel for the ongoing starburst. Without these different senses, our picture of a galactic merger would be tragically incomplete, like watching a play from the lobby and only hearing muffled sounds from the stage. The most energetic and formative moments of the cosmic dance often happen in the shadows, reminding us that the universe's greatest dramas are not always performed in the open. Hidden within the brilliant chaos of a galactic collision, some of the universe's most powerful objects are born. These are the ultraluminous infrared galaxies, or ULIRGs for short. While their name might sound technical, these cosmic titans are essentially galactic furnaces operating behind closed doors. They are so luminous that they can outshine our entire Milky Way by a factor of 100 or even 1,000. But they pour out almost all of that energy in a form of light our eyes cannot see, infrared. The secret to their incredible power and their hidden nature lies in the very dust they create. When two galaxies merge, they trigger a firestorm of star formation, a starburst of almost unimaginable intensity. This produces not only millions of new stars but also colossal amounts of cosmic soot, vast clouds of dust that fill the galactic core. The intense visible and ultraviolet light from all those newborn, massive stars slams into this dust. Instead of escaping into space, the light is absorbed, heating the dust grains to scorching temperatures. This heated dust then glows, re-radiating all that captured energy as a tremendous, overwhelming outpouring of infrared heat. It is as if you took the light of 100 billion suns and filtered it through a blanket of hot charcoal, transforming a brilliant beacon into a smoldering, invisible inferno. These ULIRGs are not just a curious side effect. They represent a critical, fleeting stage in the life of a merged galaxy. All that furious activity is crammed into a relatively small region, often just a few thousand light-years across. This concentrated energy creates an environment of extreme pressure and turbulence, forcing the galaxy to evolve rapidly. The immense inflow of gas that fuels the starburst also funnels toward the central supermassive black hole, feeding it until it awakens as a brilliant quasar. The radiation and winds from this quasar can then blast away the remaining dust and gas, effectively lifting the cosmic veil. What was once a hidden, infrared-only object can transform into a visible, dazzling quasar, a beacon that can be seen across the universe. In this way, a ULIRG is often the missing link, the brilliant but shrouded adolescence of a galaxy on its way to becoming a mature, quiet elliptical. They are the universe's most dramatic metamorphosis, playing out behind a curtain of its own making. This entire cosmic drama unfolds on a timescale that challenges human comprehension, a slow-motion ballet with movements lasting longer than the age of our planet. The journey from two distinct galaxies to a single, new entity follows a surprisingly predictable sequence, a choreography written by gravity. It all begins with that first, fateful close pass. The galaxies swing by one another, their outer stars and gas pulled into those spectacular, sweeping tidal tails. This initial encounter is not the end, but merely the opening act. Though they may appear to be flying apart after this gravitational slingshot, they are now irrevocably bound. Their mutual attraction is too strong, a cosmic tether that ensures they cannot escape each other. They enter a period of separation, but it is only a temporary retreat, a slow, arcing loop that will inevitably bring them back together. With each subsequent close encounter, the invisible hand of dynamic friction works its magic. Every pass through each other's dark matter halos and stellar populations saps a little more of their orbital energy, like a pendulum slowly losing momentum. This relentless drain pulls them into a tighter and tighter spiral, their loops becoming smaller and more frantic with each billion-year cycle. The galaxies no longer swing past each other, they begin to plow directly through one another, their cores drawing nearer. This is the final act of coalescence, a violent churning that completely erases their original structures. The two separate hearts of the galaxies finally merge, and over the next few 100 million years, the chaotic swarm of stars begins to settle. The random motions imparted by the collision smooth out into a new, stable equilibrium, resulting in a single, relaxed galaxy, often a serene elliptical. This timeline, however, is not a rigid clock. The entire process can be sped up or slowed down dramatically by the specific characteristics of the dancers. A collision between two gas-rich spirals will be a longer, more violent affair, as the gaseous friction and spectacular starbursts add complexity. A merger between a large galaxy and a tiny dwarf, by contrast, is a quick and one-sided affair, a mere snack that leaves the larger galaxy mostly unchanged. The precise angle of the initial approach, the impact parameter, also plays a crucial role, determining whether the first pass is a gentle brush or a direct, head-on crash. When we look up at the sky and see two galaxies connected by a bridge of light, or a single galaxy with strange, shell-like structures, we are not looking at a random accident. We are seeing a single, frozen frame from this multi-billion-year film. Each peculiar shape is a testament to a specific moment in the universal dance, a moment we can now understand and place in its proper sequence. The grand collisions between titans are not the only way galaxies grow. A far more common and gentle process is always at work, a quiet form of cosmic consumption known as a minor merger. This is the story of galactic cannibalism, where a large galaxy steadily feasts on its smaller neighbors. Our own Milky Way is a perfect example of this gentle predation in action. Right now, it is in the process of digesting the Sagittarius dwarf spheroidal galaxy, a tiny satellite that has been orbiting our home for billions of years. With each pass, the Milky Way's immense gravity peels away stars from this dwarf, drawing them into the vast spherical halo that surrounds our galactic disk. This is not a violent, explosive event. It is a slow, relentless tide of assimilation. The dwarf galaxy is being stretched into long, shimmering streams of stars that wrap around the Milky Way like celestial ribbons, a beautiful and permanent scar from a slow-motion destruction. These minor mergers lack the brilliant starbursts and dramatic distortions of a major collision, but their influence is profound. They steadily pump new stars and, crucially, fresh batches of dark matter into the halo of the larger galaxy, increasing its mass and gravitational reach over cosmic time. They can also provide just enough of a gravitational nudge to compress pockets of gas within the larger galaxy, sparking localized waves of star formation without the galaxy-wide firestorm. This is the cosmic dance in its most patient and persistent form. It is a continuous, gentle rain of building blocks, a process that has been shaping galaxies like our own since their earliest days. Every large spiral we see in the night sky bears the faint, ghostly fingerprints of these digested dwarfs in its halo, a silent testimony to the quiet feasts that built the universe. Your galaxy's cosmic address dictates its destiny. Whether it lives a quiet, isolated life or is constantly pulled into violent mergers depends entirely on where it sits within the grand architecture of the universe, the cosmic web. This web is not a flat, two-dimensional structure, but a vast three-dimensional scaffold, with galaxies strung along its filaments like glittering beads on an invisible string. Where these filaments intersect, they form immense, bustling cities of galaxies known as clusters. These are the most crowded neighborhoods in the cosmos, where hundreds or even thousands of galaxies are packed into a relatively small volume of space, all orbiting a common center of gravity. In these dense galactic metropolises, the dance of collisions is a constant, ongoing event. The sheer number of galaxies, combined with their slow, perturbed orbits within the cluster's powerful gravitational field, makes close encounters and mergers a statistical certainty over billions of years. It is a cosmic ballroom where the dancers are so close they are always brushing against one another, their fates intertwined by proximity and gravity. Conversely, consider a galaxy living in a cosmic void. These voids are the empty deserts of the universe, immense regions of space that are largely devoid of galaxies. A galaxy residing here is a cosmic hermit, separated from its nearest neighbors by hundreds of millions of light years of near emptiness. In such isolation, the gentle pull of gravity from another galaxy is too weak to ever draw them together on a realistic timescale. This galaxy may live its entire existence in serene solitude, its spiral arms spinning undisturbed for eons, never experiencing the transformative fire of a major collision. This profound connection between location and evolution means that by simply observing a galaxy's shape, we can read its history. A pristine, elegant spiral galaxy likely grew up in a quiet suburban filament or an isolated void, while a giant, featureless elliptical galaxy almost certainly has a violent past, forged in the crowded, chaotic environment of a dense cluster. The universe is not a random scattering of islands, but a deeply interconnected network where the largest structures imaginable directly determine the life story of every single galaxy within them. These galactic encounters produce some of the most stunning visual art in the cosmos. The Hubble Space Telescope has gifted us a gallery of this celestial violence, turning raw astrophysics into profound imagery. Look at the mice galaxies, their long, graceful tails intertwined in a slow-motion chase, two spirals forever bound by their mutual gravity. Or witness the butterfly galaxy, its wings of incandescent gas spread wide, a fiery symmetry born from a direct head-on collision. Then there is the haunting beauty of the Atoms for Peace galaxy, a nearly perfect ring of brilliant blue star clusters encircling an older, golden core, the ghostly remnant of one galaxy that plunged straight through the heart of another. Each of these iconic portraits freezes a single instant in a billion-year-long performance. They capture a universe where chaos and creation are two sides of the same coin, where the same forces that tear structures apart also sculpt new forms of impossible elegance. The delicate loops and fiery plumes are not random. They are the direct, predictable outcome of gravity and motion, a physics that consistently produces splendor from the void. These images do more than advance science. They speak to a deeper human connection. They remind us that the universe is not a cold, mechanical place, but a dynamic artist, constantly painting with the raw materials of matter, energy, and time. The cosmic dance is, in its final form, a masterpiece of natural art, an exhibition of creation written in light across the expanse of deep space. Our view of the cosmic dance is about to transform with a new generation of eyes on the sky. The James Webb Space Telescope has already begun piercing the thick dust shrouds that cloak the most violent acts of creation within merging galaxies. Its infrared vision reveals the fiery birth of star clusters and the feeding habits of central black holes in places that were once complete mysteries to us. But Webb is just the first member of a powerful new team. Soon, the Nancy Grace Roman Space Telescope will join the effort, not by staring intensely at a single target, but by casting an incredibly wide net across the cosmos. It will scan vast stretches of the universe to find rare and fleeting stages of collisions, catching the dance in its earliest steps when the first tidal streams are just beginning to form. Meanwhile, back on the ground, colossal observatories are taking shape. The extremely large telescope, with a mirror nearly the size of a blue whale, will collect so much light it can split the glow of distant galaxies into incredibly detailed spectra. This is like moving from a black and white photograph to a high-definition chemical analysis, revealing the precise composition, temperature, and motion of gas and stars within a cosmic wreck. Together, these instruments will act as a universal testing ground. The sophisticated simulations that predict how galaxies merge will finally face a barrage of real-world data, measured with an accuracy we have never before possessed. We will be able to look back to the infancy of the universe and watch how the very first galaxies began their own collisions, building the cosmic web from the ground up. And perhaps most thrillingly, in all this new data, we may find something our simulations never predicted, a new step in the dance that we have not yet dreamed of. The next chapter in this billion-year-old story is waiting to be read in the light of these new machines. Galaxies are not static islands, but dynamic participants in a billion-year-long construction project. Our journey through the cosmic dance of their collisions reveals a universe that is fundamentally creative, using apparent chaos as its primary building tool. The silent, inexorable pull of dark matter sets the stage, drawing these titans together across the void. When they meet, the result is not mindless destruction, but a spectacular reorganization of matter and energy. We have seen how these encounters unravel majestic spirals, forging them into the serene, rounded forms of elliptical galaxies. They trigger brilliant firestorms of star birth, lighting up the cosmos with the glow of millions of new suns. They even sow the seeds for new, independent worlds, as tidal dwarf galaxies coalesce from the expelled debris. At the very heart of this turmoil, supermassive black holes are drawn into a final, silent merger, rippling the fabric of spacetime itself. This entire process is a testament to a universe that builds upwards, where the largest structures are assembled from the smaller pieces that came before. The future collision of our own Milky Way with the Andromeda galaxy is not a distant abstraction, but a personal reminder that we are part of this ongoing, grand narrative. The universe constructs itself through a beautiful, relentless dance, a dance of gravity and light that we are only just beginning to fully comprehend.